Hey Engineering 150 students, sorry I can't be there with you tonight, but I know Aaron's going to take good care of you. So before you do the hands-on exercise tonight, I want to kind of give you an overview to design, to give you some things that you're probably not going to hear again in school. We'll talk about that a little bit more in a second. But so you read about design, and so tonight when I'm talking about design, I'm meaning it in the broad sense. You read a definition of design, deliberately determining how to put something together so it'll best meet the customer's need. I want to add to that, deliberately determining how to solve the problem so that it will best meet the customer's need. So when I say design, I'm talking about design in the broad sense, the type of thinking that we develop and that we use as engineers to solve problems, whether that problem is creating a physical design for someone or designing a solution. So that's what I mean this whole time when I'm talking about design right now. Okay, so here's the typical impression that you're likely to get in school about design, where someone gives you a set of specifications, requirements, you perform engineering design, and a product pops out the other side. Or there's some problem, you take your engineering technical knowledge, and that problem gets solved. It's very easy as you go through school to develop this kind of impression of what we do, about how design and problem solving really works. But it doesn't work this way in the real world, because real problems, needs occur within complex problem situations. A lot of times I refer to it as a messy, complex situation, because the real world is messy. There's all kinds of elements in the problem situation. In those elements, there's multiple interactions going on. Those interactions are very complex, and there's all kinds of dimensions. There's cost involved, there's schedule involved, there's different people and politics. All that stuff goes together to create this messy situation. And in the middle of that complex situation, there's a customer. That customer has a need. Something is not the way it should be. They want something to be different. And so they come to you, the engineer, and what they want you to do is they want you to completely satisfy their need. That's what they really want you to be able to do. Now, they may ask you for a product, but they don't really want a product. They want their need met. And it's very likely they don't know exactly what they want or what they need. They might know what they want to accomplish, but probably not even that completely, because that problem situation is too complex to know exactly what they want to solve the problem. They know a piece of it, but you're dealing with a system with a lot of different parts. It's hard to know everything. No one can know all the pieces. And also, they don't always know the implications of what they ask you for. They know their part, but they don't know how all the other interactions can come. So that customer they need you. They need your help. And here's really what they want to have happen. That customer wants to be able to come to you, the engineer, have you study their complex problem situation to really understand their need and define the real what. From that, you'll be able to create requirements. Those requirements will drive engineering design, which will create the product that satisfies their need. That's really what the customer wants. So you see, but for an effective solution, that top portion of understanding their situation, understanding what, defining requirements, has to be done. You see, over and over again, we hear that industry wants engineers that can assume responsibility for understanding and delivering the what. That's what they're going to want out of you when you go to work. Now, traditional engineering education trains you in that bottom part. That's really where you get trained and what you focus in. So I encourage you, soak this idea in now of this understanding what, defining requirements, because you might not hear a whole lot about it again until you go to work. So let me show you how this really works, like if you're an engineer working for a company. So there's some messy situation and there's a customer and they have a need and they sort of study their need and determine that, you know what, we need this in order to solve it. And so then typically what they will do is they'll come to a vendor, another company, a company like you work for, or you heard Daniel talking. Boeing came to Tandem Lock to help them with a particular thing. They said, we want you to design this for us. And so then what'll typically happen with a large scale system is there'll be a project engineer, and that might be you. And so you and the vendor will work together to understand the need and define everything necessary to satisfy that need. That'll get expressed in what we call requirements. So then there'll be a formal meeting where those requirements are reviewed and the customer and your company, you both agree to them. And then that's a legal binding document, those requirements that define what each of you are going to do. Okay, so then the vendor, your company, goes off and does design and production. So what's going to happen is your company's engineering team goes through and starts designing the thing. But here's what happens. Those requirements that you created back here, those requirements represent the customer to the designer. It's very possible that the people doing the design have never met the customer. They've never been in the customer's plant. Only thing they know is what you have represented about the customer to them through the requirements. That's why requirements are such a big deal. Again, you heard that as Daniel talked. What he got was a sheet with requirements. He didn't know what was happening with it, where it was going. So if those people didn't do a good job defining those requirements, what they got back from Daniel wasn't going to do the job. And then once they design it, they have to have it built. Well, you come up with engineering specifications as you're designing, and it's those specifications that are representing the customer to that person that's building to make sure that it's built right to satisfy the design, which then finally satisfies the need. So then your design is verified and it's implemented and the need satisfied. So that's the big picture of how this whole designing a product works in the real world, whether it's a rocket, whether it's a car, whether it's a new biomedical device. That's the big picture of how this whole design idea really works. So from the book, you saw this representation of kind of the traditional engineering design approach, the steps, and you read the overview of these. So if you look at that compared to what really happens in the real world, all this right here, that's the requirements definition. That's those top two pieces. This part right in here, the design and production going on in that company, that's these last steps with conceptual design all the way going through. So the blue, what I call requirements definition, the red is that typical view of engineering design. Okay, so we saw that industry wants you to be able to do this requirements definition piece. Because you see, requirements tell the designer the lines that they have to stay within. It gives them the bounds. Requirements tell the designer what is needed to satisfy that customer's need. That's why requirements are so important, and learning how to do them is really, really important. And understanding what is the first step to really effectively designing requirements. So that whole what versus how, it's critical for you to try to develop that ability and just realize this working with the customer is what industry wants you to be able to do when you get out, even though your school may only focus on this piece right down here. Like I said, I encourage you to soak this in now and begin to develop that ability and understand and look and see how important it is. Okay, so now what I want to do real quick is give you 2 tips about how to design well that you'll use on your semester project, and then 1 tip that you'll use later in other classes. Okay, first tip is this. When you're designing, you are solving someone else's problem. So you need to get to know them and include them as much as possible during the design process. You're solving their problems, so you need to include them. Tip number 2, design is real. You must touch it, feel it, imagine it. You can't just stay at the keyboard when you're designing. You need to get in the middle of it. Okay, now your semester project is going to stop with step 2. You're going to do a conceptual design. As you move on in your engineering courses, you will get into this detailed design where you work out every bolt, how big the bolt needs to be. As Daniel was talking about, will the bolt rip out? Or if you're in chemical engineering, all the different pieces of the chemicals, how much that have to go together, or biomedical, whatever type of engineering, you will do this detailed design work. This last tip is for when you get to there. And here it is. Design is about details. Dive into the necessary details and don't leave any important stone unturned. Students sometimes try to do design at the surface. They don't dive in. They try to multitask. No, focus and dive deep into the necessary details. Also, use all of you. And here's what I mean. When you're designing, doing the details, use your experience. Apply what you know. Apply what you've seen. Design is very much like a musician. Different musicians have a style. That style was created by all the people that they listen to. People who really know music can hear that. Well, you're a designer. All of your experience is going to go into your design. So use that. The other thing is use your research ability. Learn new things. Look at new fields. Research the details. If you're not sure about something, go research it. And then the last one is use your technical ability. When you need to, do the math. You're wondering, okay, will this kind of material melt when it goes in the stomach? You're a biomedical engineer. Go do the math. Go look, go do the calculations. Again, students very often try to do detailed design without jumping into the details, without using the technical knowledge that they have. So when you get to that spot, please use all of you and do these things. Okay, so now I want to transition one last thing. The Stanford Design School has an idea, and it's not just them, but they've done some good work in it, called Human-Centered Design. It's design that's used to design large things like large-scale energy systems or large-scale transportation systems. So it's an approach for design. But there's parts of it that I think can be very, very effective for engineering design. So I want to introduce you to it. So hopefully you'll carry these ideas with you as you move on through school, as you become an engineer, and you'll be a better designer for them. So again, here's the typical engineering design process. The human-centered design, their first 2 steps are empathize and define. The whole idea is that you're solving someone else's problem. So you need to understand the person and their need. Engineering design, we typically would say you need to understand their need. The human-centered design brings into that, no, you need to understand the person, because you really can't understand their need or give them what they truly need if you don't know some things about them. So they talk about viewing the users and their behavior in the context of where what you're designing will be used. Interact with them, engage with them. Then at the conceptual design phase is where I see the other part of design thinking coming in. And here's what they say is their step number 3 is ideate. We would call that brainstorming. But again, the key difference is they say you need to generate lots of ideas, that you never stop with your first idea of how to solve a problem, that you have divergent thinking, just crazy ideas, before you then begin to hone in and create some good new ideas, because you got to break out of your old thinking. Step number 4 is they say prototype. And again, here's the difference with traditional engineering. In traditional engineering, when we say prototype, we mean you've designed the whole thing and now you build one and you try it out. No, what design thinking is talking about is You're never going to find the one right answer, so try something. When you have an idea, you're like, I wonder if I could do this. Well, build a rough prototype of that. Use popsicle sticks, use cardboard, to try that one idea out. Don't build the whole thing. Build a piece of it. You have an idea, try it. And try early, try often, and you're going to prototype your way to a full solution. So that's what they're talking about when they say prototype, very rough prototypes that you're learning from. And then another difference, their step number 5 is test, is when you're trying out an idea, let the user interact with your prototype. But again, here's the difference. As they interact with your prototype, watch them. Learn about them and learn about your need. What we typically do as engineering is we create a prototype, we give it to the user for them to try it, to validate it. Is this good or not good? What design thinking says is no, you're not validating, you're learning, you're probing for more insights that you can use to improve your design. You're not a salesman trying to show how good your design is, you're an anthropologist learning. So then after the testing, that leads you back to ideate some more, and you keep looping, learning, going closer and closer to a final design until you have a solid conceptual design. Then the goal is to understand and satisfy your user's need. So then from there, you would come back into the engineering design process and then go into detailed design. So that's how I see these two schools of thought, if you will, really kind of coming together and improving your ability as an engineer to design. So you're going to learn by doing today. You're going to practice human-centered design by being led through it on a simple problem. So for homework, I asked you to think about the last time you gave a gift. So here's what's going to happen. You're going to get a partner. You're going to be led through that Stanford design thinking process to design the next gift-giving gift for your partner. You're going to work with your partner. They're going to tell you about the gift that they gave, and you're going to help them design the next gift that they gave. But when I say next gift, don't just think about the gift itself. Think about that whole gift-giving experience. That's what you're designing. So a video is going to lead you through the entire process. So pay attention, follow the instructions, have fun, and learn. That's what I want you to do. So here's the process that the video is going to step you through. So number 1, it's going to step you through interviewing your partner to understand about them, the gift giving. You'll get more instructions. The video will lead you through exactly what to do. I'm giving you an overview. Then you're going to have a chance to go back and interview them some more, 8 minutes. You're going to capture your findings in 3 minutes. Then you're going to have 3 minutes to define your problem, your what. Then from that, you're going to ideate. You're going to sketch as many ways as you can to solve their problem. Then you're going to share your solutions with them. You're going to learn from that and then go back and reflect and generate some new ideas. Then you finally will build a rough prototype that you then will share with your partner and learn from. So that's the process that you're going to go through tonight. At each step, you're going to have a handout. You'll write on your handout. It'll structure, and the video will tell you exactly what you're going to do, and then it'll have a timer go and let you do it for that many minutes. If I don't say it again, when the timer starts, the music can be a little loud, so Aaron might need to turn the volume down while you all are actually working. Okay, so get your handout, get with your partner, and when you're all ready, start the next video, and let's go and practice engineering design.